Very exciting session in front of us. My name is Helena Rubinstein Dunlop and I'm from University of Queensland in Australia, down under. Our first speaker is invited speaker Andrea Aiello. There we go. Correct. And he will be talking about ubiquitous photonic wheel.
Thank you very much. Thank you very much. I would like also to thank the organizer for the nice invitation, and especially Giovanni for all the support in these days and the nice atmosphere that he created. So today, as you can see from the title, I would like to talk about the photonic wheel. What is this object? Well, before going in detail, I would like to stress that this work is made at Max Planck Institute for the Science of Light in Erlangen, and is made in strict collaboration with the IMIC group, so Peter Banzer and collaborator as Thomas Bauer that gave a talk yesterday. So the main topic of this talk is angular momentum of light, as you can guess from the title of our meeting, right? So there are, for mechanical systems, everyday systems, there are two kinds of angular momenta, longitudinal and transversal. So we speak about the longitudinal angular momentum of a moving object when the angular momentum is either parallel or anti-parallel to the direction of motion of the object itself. And we are very familiar in everyday life with these systems, like the propeller of an aircraft, or a marine propeller, the same principle. Or we have even an example from biology. So there are the rotary seeds that spiral when falling down from a tree. So in all these cases, 1, 2, and 3, we have that the motion of the object, say the airplane in this direction, is parallel to the direction of the angular momentum of the here of the propeller, here of the wings of the seed. But we can also have a transverse angular momentum. So an angular momentum which is directed in a direction orthogonal to the motion of the object itself. So for example, this happens every time we use our biro to write, or for example, when we go by bike, and then we proceed hopefully in a straight direction, but the angular momentum of the wheel is directed orthogonal to this direction. Well, for light, we have exactly the same phenomenology. So we can have a longitudinal angular momentum of light, which can be, of course, in this case, is associated, I'm talking about spin angular momentum, is associated to circular polarization. So you can see here, this spike represents an oscillating electric field, and the motion of this electric field is similar to the motion of the aircraft propeller. So the electric field propagates in this direction, and the electric field spiral in a plane orthogonal to the direction of propagation. In this case, therefore, the angular momentum is along this direction. Vice versa, there are some other initially thought exotic field configurations where the electric field rotates in a plane containing the axis of propagation. In a terminal jargon, this plane containing the axis of propagation is called the meridional plane, just to distinguish it from the transverse plane. So, as you can see, for light fields, we can have both kind of angular momenta. And this initially, when we started some years ago working on this, generates some surprise reaction, because it is common wisdom that from electromagnetism that photons, quantum of light, can have only a component of the angular momentum either parallel or anti-parallel to the linear momentum. So the so-called helicity of photons. But of course, this is true only for plane wave photons. And so if we want a trivial solution of Maxwell equation. But vice versa, in the recent years, with the growth of interest about nanophotonics, people was producing and studying very complicated electromagnetic field configurations. And when you have complicated electromagnetic field configurations, so very different from plane waves, then the spatial and temporal structure of the electric field may be very different from the one of a plane wave. So you can have a strange behavior. Here you can see the motivation for the title of the talk. So photonic wheel. We call photonic wheel states of light where the electric field rotate like the spike of a bicycle, so in a meridional plane. And there are several interesting effects that mostly studied by people who is sitting here or in the other conference, linked to the transverse angular momentum of light, like the spin-Hall effect of light, first studied by Onoda, Biok, then experimentally by Kwiat, the geometric dynamics of spinning light, again Biok, Zeldovich, other. This is our work we did in Erlangen with Peter Banzer, so the so-called geometrical version of the spin-Hall effect of light. Then the very recent interesting work about directional coupling in optical fiber and so on. But unfortunately here I don't have time to talk about all these interesting applications, but tomorrow you can listen to Gert Loik's talk, and he will give a better overview about this phenomena. So since I don't have so much time, I go directly to the goal of this talk. So as I told you, angular momentum of light can exist in two different forms, or can have two different manifestations, either longitudinal or transverse. While we know everything about say longitudinal angular momentum is very well known, so association with circular polarization for vector field, or say vortex beam in the case of scalar field, much less is known about typical characteristic of beams exhibiting transverse angular momentum. So our goal was to find, say, some minimal and sufficient conditions that a wave field, for wave field we mean an arbitrary solution of the Helmholtz equation, that satisfy in order to exhibit transverse spin angular momentum, density in general, and then particular configuration even integrated. So we start really from the basic. We consider generic electromagnetic vector potential, and then we consider a plane waveform of this electromagnetic vector potential. So first we impose on this function the D'Alembertian condition, so it must be a function satisfying the wave equation, and this produces the well-known linear dispersion relation in vacuum between the angular frequency and the modulus of the wave vector. Then the second condition we must impose is divergence free. So in this case, this means that k dot n, where this is just an arbitrary vector specifying the polarization of the field, must be orthogonal to k. So this is the main interest of this of our work, this relation. Of course, this relation has a trivial solution, the null solution, and of course it's not interesting. But then the next step, the non-trivial solution have, say, two non-zero components, or if you prefer, just say one zero component. Of course, there are three possibilities to have a zero component, so you can have the longitudinal zero component or the two transverse zero components. And this simply means that, so given the arbitrary k vector, you can define a 3 vector, and 1 and 2 and 3, which are either in the, say, zy plane or xz plane or xy plane. And of course, the 3 vector form an overcomplete system of base for the transverse space. So, and this configuration are well known for guided modes. For example, in Hall of Guides, there is enormous literature in microwave, for example, about this. So, for example, if you choose the n1 vector and you associate this k vector, you get the so-called TE modes of a rectangular waveguide, or vice versa, if you choose the 3 vector and this corresponding k vector, you get the so-called TM modes of a rectangular waveguide. In this work, we are, of course, interested to the solution of the kind of the third kind, because we want to have a transverse component of the field and a longitudinal component of the field. So from now on, we focus on this kind of solution. So we go back to our plane wave, which has this simple form, and then we just make a little algebraic game. So instead of writing the k vector component in this way, we write in terms of derivative of the plane wave function. Of course, an arbitrary field can always be expressed as a superposition of many wave functions. So given the same formula, this one that we saw here, here we can replace the plane wave by an arbitrary scalar field, which is a solution of the Helmholtz equation. Then we end up with this simple form for the electromagnetic potential. From this electromagnetic potential, we immediately can calculate the electric and magnetic field. So as you can see, this electric field has one null transverse component and has a second non-zero transverse component and a longitudinal component. So in principle, this is a good candidate to generate a photonic wheel, because in order to have a photonic wheel, we need to have a longitudinal and a transverse component of the electric field in order to allow for this rotation. And so in this case, this choice of the entry vector, we got a motion of the electric field in the YZ plane. So let's go further. Let's try to develop this idea. Then we focus on monochromatic fields. There is no need to go to introduce complication with non-monochromatic fields. And the physics contained all in this monochromatic case. So you can write this field as the product of spatial dependent amplitude and the oscillatory exponential complex exponential behavior, and then we write this complex function we decompose simply in a real part and imaginary part. Then we know that the real electric field, the one that we measure in our laboratory, is just given by the real part, and by using standard formulas that you find in chapter 1 of Born-Wolf, for example, you write this electric field as the sum of two vectors, P and Q, which are not necessarily orthogonal, which multiply two functions in quadrature each other, so they are pi over 2 out of phase. If we substitute this function in our expression for the electric field in terms of the potential vector, we simply find this simple expression for the vector P and Q. Why we like P and Q? Because if you continue your reading of the Born-Wolf, then you find what are the conditions that P and Q must satisfy in order to generate a circular polarization. Of course, in Born-Wolf you will find this reasoning for ordinary circular polarization, that is a circular polarization in the xy plane, so in the transverse plane. What we do here is simply to apply the same concept to the meridional plane, so to point in the meridional plane, so the yz plane. So the two conditions that P and Q must satisfy in order to generate circular polarization is that they must be orthogonal and they have basically have equal modulus. So if you translate these two equations in terms of the u and v, so the real and imaginary part of our scalar field, you find these two relations which should be satisfied in the generic point R0. So the one of you familiar with complex analysis will recognize immediately that these are the Cauchy-Riemann conditions that guarantee that a function is holomorphic or analytic. So we were looking for this condition, as we said in the beginning, a minimal sufficient condition, and initially we didn't know exactly what we could find, but we were very pleased to find such a beautiful condition. I mean, a priori, who would imagine to find the Cauchy-Riemann condition linked to the circular polarization in the meridional plane? So we found this, and we were very happy with this. So I try to 5 minutes still. Okay, I try to skip something. So I prepared two examples to illustrate this. One is a Bessel beam. So if you take as a scalar function a Bessel beam, you are all of you very familiar with this notation. Then you can calculate the real part of the electric field, and if you select the specific point where the Cauchy-Riemann condition give you the circular polarization, then you can see here are 3 snapshots in 3 different times of the electric field distribution in the meridional plane, yz plane. So you see that as the time goes from left to right, the electric field vector make a rotation exactly in the meridional plane, because has a transverse component, a longitudinal component out of phase, because you have a cosine and a sine propagation. And of course you can calculate all the dynamical quantity, but I will skip this because there is not enough time. It's only important to stress that there is an orbital part of the linear momentum and the spin part of the linear momentum. And okay, here I can just skip. And in order to find these points where the Cauchy-Riemann condition are satisfied, we can simply, instead of applying the Riemann condition, simply calculate the Stokes parameters expressed in terms of P and Q component of the vector, as was introduced by Mark Dennis in this nice work, but now calculated in the meridional plane. So we found this apparently complicated equation, but when we calculated for our Bessel beam, they became much simpler. Then the condition to have circular polarization in meridional plane is simply to have S3, the Stokes parameter associated to circular polarization, equal to S0. So basically you find that alpha must be equal to beta, so the ratio between these two quantities must be equal to 1. So if you plot this ratio, you find a nice figure in the transverse plane with quite a complex rich structure here, which is not singular. That is, the function itself is continuous, the first derivative is discontinuous. But if you just take a section of this nice construction in the x equals constant, then you see here the red curve is the intensity of the beam as 0, the blue curve is the circular polarization component in meridional plane, and the orange curve is the ratio. So you see you have these points where the ratio is 1 or minus 1. So this means that if you put your detector in these points, in the meridional plane, you will find exactly a circular polarization in the meridional plane. So a purely transverse angular momentum. As a second quick example, since we claim that our mechanism is say, universal, that is, I can explain both propagating field, evanescent field, and whatever you may imagine. So we have a second example with evanescent waves, the form that all of you know. So this wave propagates along the y-axis, exponentially damped along the z-axis. Again, you repeat the same calculation, calculate electric and magnetic field. And again, this is very well-known pattern. Just a little, I stress a little point. You can have a much nicer pattern with evanescent wave, permitting evanescent wave to interfere each other. Why we like this? Because in this case we can model almost at our will the relation between, say, the amplitude, the linear momentum, the spin part, and the linear momentum orbital part. This may be interesting for some application. Unfortunately, there is no time here to go ahead. So simply again, you calculate the standard dynamical quantity, and again you calculate the Stokes vector as we did before, and you find this very nice and simple relation for the condition to have say transverse angular momentum or photonic wheel, as we call it. And then you see that whenever the say evanescent parameter zeta is bigger than 1, then this condition is almost always satisfied. And this is exactly what you saw, for example, in some example presented yesterday by Konstantin with the evanescent waves, where you have this purely transverse spin angular momentum. So you see that with our general formalism, we can reproduce exactly this result. So in conclusion, what I hope to have conveyed to you today is that transverse spin angular momentum density is not such an exotic quantity as it was thought some years ago. Actually, it's quite common. You can have in many different kind of beams, and it's very useful because I show you very, very quickly some application of this. And as we found with this Cauchy-Riemann condition and so on, is a topic that still may reserve surprise, and we are still continue investigating along this line, and we have already some other interesting results. So just to say that the work is done in my group, the optics theory group in division logs at Max Planck, and with especially I collaborate on this topic with Falk Toppel. And with that I can conclude. Thank you, and conclude my talk.
And we have time for a few questions. Yes, please.
I can't see the connection between analyticity and momentum. could you explain? I mean, why is there any Cauchy-Riemann equations have anything to do with it?
Well, why? I wish to know why. That is, it was a kind of unexpected bonus that we get. That is, we were simply looking for this condition that guaranteed the existence of circular polarization. And then when we plug in this relation the expression for the field, automatically we got the Cauchy-Riemann conditions. These are almost the Cauchy-Riemann condition. What I mean? This must be verified in isolated points, R0. So this doesn't mean that these U and V are per se harmonic function everywhere on the YZ plane. So the U function is not an analytic function. Just in isolated point, verify the Cauchy-Riemann condition. However, and you can find the detail in the article in the archive was there. However, you can imagine to build functions which are analytic everywhere in the YZ plane. But of course, this harmonic function by definition cannot be physical in the sense they are not normalizable. But this doesn't mean that they cannot be realized. I mean, for example, also Bessel beams are not normalizable functions. Still, we do good approximation in lab. So in principle, this Cauchy-Riemann condition can be really also extended not to isolated point, but to really holomorphic function in all the YZ plane. So, and again, I don't know if you can say why. I can tell you how, but not why.
Any other questions? If not, okay, go ahead.
Is there a sense of, if one were to set up an experiment and want to use standard polarization optics, is there a sense of how to use a wave plate or things of that sort, which is traditional polarization schemes, for something that's traversing, polarizing this meridional plane?
Well, for example, in the example presented yesterday by Konstantin Bliok, he considered the example of two interfering plane waves. In the interference pattern of two interfering plane waves, you get some fringe where this phenomenon appear. And of course, here is you can reproduce also this result just by summing two of these solutions. So, in principle, of course, two plane waves don't exist in nature, but other way are, for example, interfering two beams in a high numerical aperture microscope, as Thomas did, and there you get a similar transverse angular momentum. Actually, Peter and Thomas, they've measured with a special technique that can resolve both amplitude and phase of the field this photonic Will behavior in the focus of this particular shaped two lobes beam.
Okay, let us thank Andrea for the talk.
Thank you.
Our second speaker is Gabriel Molina Teresa from Macquarie University in Sydney, Australia, and he'll be talking about control of the interaction of photons with nanostructures via the angular momentum. Gabriel.
Sure. I don't see a screen here, that's why. Good. Thank you, Halina. Well, so, as you know, I'm in Macquarie University, which is in Sydney, Australia. I moved there 5 years ago, and when you start a new group, you always wonder, how are you going to contribute to science? What are you going to do, which is different than the other people, or how to help other people in their research? So I decided to join or to explore the interface between two different fields. One was nanophotonics, and the other was quantum optics. And why I thought that that could be interesting for the broad community or for the people is because my understanding of how focused fields, electromagnetic fields, was not very. There were things that they didn't understand very well from that physics. Actually, we've seen that over the last days we've been discussing about how to separate the angular momentum into the orbital part and the spin part and all that. And actually, that kind of thing is only relevant when you have highly focused fields, because in the paraxial approximation everything is clear. The interaction between these fields and nanostructures or atoms or molecules is also very interesting and something which is worth exploring. And using all the power of quantum optics into that's something which I thought that it deserves a chance. Actually, in my opinion, so nanophotonics can give a lot of opportunities for the quantum optics community, because there's a lot of things which have been done in the nanofabrication, and actually we can use maybe smaller sources or smaller quantum memories for quantum information. And on the other hand, I think that quantum optics can help the nanophotonics community as well, because there are techniques in quantum optics or in quantum information, like quantum metrology, which could help us to understand better these nanostructures. So to give you a flavor of that, I'm going to mention one thing that we've been working on since in quantum plasmonics. Okay, so most of you know what plasmonics is. Is working with metallic structures which present some resonances at the optical frequencies. So these are in plasmonics. So one of the revolutions in plasmonics in the last, let's say, 20 years. There have been many revolutions in plasmonics over the last 100 years, but it's due to the new fabrication techniques. No? So now we can fabricate structures which are comparable with the wavelength of light, or even smaller, and pattern them in many different ways. Okay. So actually, these plasmonic structures present a high coupling with light, which makes that their scattering cross-section is much larger than their actual size, so that the interaction with light is very, very strong, which gives us an opportunity to use them for many different applications. These plasmonic resonances, when you think about them, actually you have all the electrons, let's say in the conducting band of your metal, which are oscillating collectively at the optical frequency. So this is a mesoscopic state of light when you have these nanostructures. Okay? Sorry, a mesoscopic state of matter, where you have all these electrons just oscillating coherently. Could be interesting to use that maybe to store light, or to store actually the information of a single photon in these things. But unfortunately, plasma typically relax very quickly. They have these electrons, they hit the ionic lattice and then they decohere, so they are not. So they don't provide. They cannot provide a useful quantum memory at this point. So to give you a flavor of how good the fabrication facilities are these days, well, this is a structure which we have done in my group. So if you go to the conference next door, you would see stuff which is much more advanced than that. Okay, so this is very basic, but you can see these are structures which has a size of 200 nanometers more or less, and we can have features which are of around 20 nanometers. Okay, so this is the kind of things that you can do to pattern these kind of structures, these metallic structures, with this kind of precision. So our approach in quantum plasmonics is so what we are trying to do is avoid the dipolar modes. We've seen that in nanophotonics, all the dipolar modes are very broad, while the multipolar modes tend to be much more narrow. So this could give us a way of avoiding this fast relaxation. Actually, now in the world, in our group, we have large capabilities to engineer the spatiotemporal properties of photons. So we can do entangled photons which are entangled and correlated in many different degrees of freedom. And maybe we can explode that just to excite different resonances of our metallic nanostructures. And well, another thing is that we should try to avoid all possible ways of relaxation from these structures. And one thing that we've been considering is to use them in a levitated setup. Okay, so that in this way you will avoid any, as Kishan was explaining earlier this day. Okay, so you will avoid any relaxation through the surface or any other contact with other things. And yeah, I'm not going to talk about this, but this is such a cool image that I thought that I should put it here. Okay, so what you have here, this is a small nanodiamond. This is a 100 nanometer diamond which is floating over, I don't know if you see it very well, But this is a microscope slide, okay? And this is just being held by light. This is that's part of our levitation setup, and we're now currently using to control the optical forces on these small diamonds. Okay, that's the thing that we've been working a lot these years. You know, you've seen that in our papers. So these are nanoholes which are drilled in metallic surfaces, so in gold. We can drill them with different sizes and everything. And why we chose nanoholes because they are very simple structures, and we can analyze them and understand how is light interacting with these structures very easily. Still, they're non-analytical, so you don't have an analytical solution of how is the interaction of light with cylindrical structures. So, well, one thing that could be it was a kind of a surprise, and this happens when you focus these kind of fields, and you have to consider the full electromagnetic structure of electromagnetic fields. Is that so when they interact with nanoholes? So, for example, the polarization matters a lot. Okay, I presented the preliminary results on this like 2 years ago in the last ICOAM, so it's good to have them published now. What we are doing here is using vortex beams, and we're just changing the circular polarization of the vortex beam. Okay? So we have a vortex beam with L equal 1, orbital momentum 1, and a right circular polarization. And we're focusing it through a nanohole, and then we're just changing the circular polarization to left, okay? And focusing on the same nanohole, okay? And what I'm showing here is the difference between the transmittivities of these two parts. So actually, this is a measurement which is done routinely with molecules, which is it's called circular decreasing. Okay. So and actually, circular decreasing is associated with the chirality of your molecules. Here, of course, we don't have a chiral structure. So this hole is completely mirror symmetric. And still, you can see that you have some circular decreasing. So this is a difference on transmittivity with from the two different polarizations. These are the measurements for a Gaussian beam. Okay, and you can see that there's no circular decreasing, so there's no difference of absorption. So it's clear that we're breaking the symmetry by using a circular vortex beam. Okay, so but it's still interesting that in the paraxial approximation, the only thing that besides the polarization, but the only thing that changes in these vortex beams are the phase. Okay, so you can see that the intensity is completely symmetric. The thing is, of course, when you focus those fields, the structure of the fields when they are focused are very different. Okay, so this would be one with right circular polarization. This would be with left circular polarization. And you can see that, for example, in the Z component of the polarization, they are very, very different. And actually, what is more important is that the total angular momentum of these two fields is completely different. Okay, so one is 2, while the other is 0. So they are not related with any mirror symmetry or anything. They are just completely different fields, and they will excite different resonances on the nanoholes or in any other structure. So this is kind of the reason why these two different fields have different properties when interacting with the nanohole, and they can give different transmittivities. So now I think that we understand kind of well how is the transmission through nanoholes. And just to give you a summary, okay, so if you label your modes with the angular momentum, total angular momentum, and your and the helicity, which in the paraxial approximation is related with the circular polarization, what you see is that, of course, because your structure is cylindrically symmetric, the angular momentum has to be conserved. Okay, so this mode is going to change into two different modes, but with the same total angular momentum. And the thing that it's the total angular momentum is important because this is the only quantity which is related with cylindrical symmetries. This other parameter, lambda, which is related with helicity or the circular polarization in the paraxial approximation, is going to change. Okay? So it's going to go from the original value, or you would have another mode with the opposite value. So things that we know is that, for example, just because of the mirror symmetry, the amplitude of this mode when you start with m lambda has to be equal to the amplitude of the mode which has minus m and minus lambda. Okay, and the same for this other one. These are, so what I'm presenting here is the ratios of b over a. So that's the the square of b divided by the square of a. So that's the total intensity of the mode with the opposite helicity compared with the mode with the original helicity. Right? And well, these are the results with a Gaussian beam. So you can see here, I'm not sure if you see the scale, but this is like 30%. Okay? And these are from 200 to 400 nanometers. What is interesting is that when you use angular momentum 0, so you see that there's a dramatic change here, okay, in this scale. So here you have like 400. That means that you have 4 times more power in the opposite helicity mode than in the original one. Right? Or you can have up to 4 times. Here you have just 100, for example. So you have just the same density in this mode than in this one. These features here, which don't appear here, they're very interesting, and we don't understand them. We don't understand them at all. So we're still trying to understand why these features appear when you excite them with these kind of modes. You can see some of the theory of why this happens and how is related the helicity to the duality symmetry in these papers here. So can engineering quantum states present a difference in this kind of systems? Okay, so I'm giving you an example where using 2 photon states can be interesting. Right? So what I'm showing you here are the 3 possible states that you have when you combine 2 photons with total angular momentum 0 and either positive 1 or minus 1. So here you would have 2 photons with helicity 1 minus 2 photons with or 2 photons with helicity minus 1. So this would be an entangled state. Here you have 2 photons with 1, 2 photons minus 1, but the phase between these 2 states is plus instead of minus. And here you have 1 photon with one helicity and the other with the other. Okay. Interestingly enough, so from these 3 states, this one is mirror antisymmetric, while the other 2 are mirror symmetric. Okay. So when they interact with the nanohole, this one has to be invariant. Okay. There's no other way of going to the other 2 because of the mirror symmetry of our system. So this is an example of quantum interference, but at the nanoscale. So the typical quantum interference that you would see is this kind of thing, which is called the Hong-Mandel effect. Okay, where you have, for example, 2 photons incident in a beam splitter, and then either 2 go in one direction or 2 go in the other. While you can never have these cross coincidences because they interfere destructively. It's a similar thing what happens here, but just using the symmetries of our system. And importantly, quantum interference is at the basis of any quantum metrology that you want to do. So this is this funny thing which is disappearing. This is our source of entangled photons. These are some details of that. If you're interested, you can ask me later. But one thing that you should know is that this kind of source has spatiotemporal entanglement, which means that different frequencies appear at different angles. This work has been done by Nora Tischler, one of my PhD students, who is now in Vienna, and Alexander Busset. I'm not going to give many details about that, but what we are doing with this source to test it was doing many Hong-Mandel experiments, but with a difference. So what we were doing is also changing the temperature of the crystal, and this was giving us some kind of autocorrelation in the frequency. So this is an example of what you would get when you do this kind of Hong-Mandel experiment. Okay, so you delay 1 photon with the other, so they arrive at different times at the beam splitter, and you also change the temperature. Okay, and what you see here is the different coincidences. So when they're to get where they are arriving together at the beam splitter, they never will exit through two ports. They will always go together. Okay, so when they're delayed, then you have some coincidence. What we can do with this kind of technique is reconstruct the temporal correlations of the photons. So what you see here is that this is something which is typically complicated because the detectors don't have enough resolution. So you can measure easily the frequency correlations, but not the temporal correlations. And what is interesting for our community is that when you use Lagrange-Gaussian modes, then actually you can change these temporal correlations a lot. So in this case, this dip has become maximum. And the temporal correlations, you see that they present a dip. So two photons never arrive at the same time. Well, so the question is, how close are we to getting these two photons through the nanohole? We are very close. So this is an image taken with an intensified CCD camera where you have where the two photons are going through the same nanohole. So now the question is whether we will find the same Hong-Kong-Mandel dips. And thank you very much for your attention.
Thank you, Gabriel. Any questions for Gabriel? Go ahead, Thomas.
I don't quite get how you define your circular dichroism with the beams, because I would imagine if you choose the beams and want to get something like circular dichroism and entirely focused beams at that point, then you would change the spin as well as the orbital angular momentum, because then you get exactly the same field, just with a different phase front and with a different velocity of your light field.
Yeah, we had a lot of discussions. I mean, so this is a little bit of semantics, okay? But if we went to the definition of circular dichroism, which was given in the book of Barron, or you can find in the Wikipedia, and the only thing that they change is the polarization of your beam, okay? So they keep the beam the same, and then you change the circular, the right or left circular polarization of your beam, then you measure the absorption and transmittivity. Now, if you want to test for chirality of your molecule, then that's a different thing. Okay, then it would be better if you do it that way. But we were not testing chirality of our hole. We knew that it was circular. So.
What is the physical meaning that you get from the two different beams that you send in? And
oh, that's very interesting. So actually, I think that it provides more information because it's giving you the relative intensities of the different multipolar modes that you are exciting in your
But you use two different beams.
Yeah, exactly. No, you
you
use two different beams, but they have which have different expansions in the multipolar modes. Okay, because one has total momentum 0 and the other has total momentum 2. So with the total momentum 2, you are never going to excite multiples of order 1 or 2. Right? So I mean, you can get. I think that it gives you some more information, but in this case, it was just a matter of seeing that how these two modes were interacting differently with the structure.
Okay, thank you very much, Gabriel.
Thank you.
That's a little change in the program.
Something to this or
no, just laser pointer.
okay, so
I got it. Okay.
it's a bit it's a okay, the slide don't know why is it cut off from there?
It's a question of resolution of the screen.
It's cut off kind of. It's strange, and yeah. So this paper was just updated this morning to be a talk. So I prepared the slides just this morning before it's good enough. Okay, very good, thanks. Yeah, so my name is Feng Li, and I'm working at the University of Sheffield Department of Physics and Astronomy. And this work was done during collaboration between University of Sheffield, University of Oxford, and University of Cambridge. And the research group at Sheffield, led by Professor Maurice Skolnick, is mainly focused on low-dimensional structures and materials by semiconductors. So in this group, we study quantum phenomenon based on solid state optics circuits, and also another very important study is to study optical macrocavities with semiconductor materials. And indeed, in these optical macrocavities, there are a lot to study, and you can create exciton polaritons, which shows condensation, superfluidity, and especially we can create vortices in this exciton polariton, quantum light fluid, and things like that. So there are actually a lot of studies on optical vortices inside solid-state systems, semiconductor systems, but which is an interesting part of these macrocavity studies, but probably not is not very familiar with this optical angular momentum. But I think definitely these two communities are one like us on optical angular momentum and the polariton communities. There is a big chance to enhance the communication between us and to increase the communication and to understand different fields. So in this talk, first I will talk about spin-orbit coupling in the in optical macrocavities, and then talk about what the other observations of those spin vortices in macrocavities, and then propose the possibility to manipulate a coupled orbit and spin states. So optical macrocavity, a semiconductor one, is basically this kind of structure. So it's grown by molecular beam epitaxy. First, a bottom DBR, and then an active region of the cavity which can have quantum wells, which has excitons. Then you have a top DBR. So those DBRs called distributed Bragg reflectors. It has very high reflectivity, so it can confine light in the macro scale, which is the cavity length is close to the wavelength, and the light is confined inside the cavity, so it's quantized in this direction, and it can only move like a two-dimensional optical gas in this macrocavity. And as we know that for S-polarized and P-polarized light on the interfaces between different materials, there is a difference in reflection and transmission and also the phase changes of S and P-polarized light. And this introduced a TE-TM splitting. If you look at the in-plane wave vector of the optical mode, which moves inside this planar cavity, this TE-TM, this difference in S and P polarized mode, it introduces a TE-TM splitting, energy splitting, with the in-plane wave vector of K inside this macro cavity. And this serves as what? So once you have T and TM splitting in the macro cavity, so the eigenmodes in this cavity is TE and TM. So when it splits, if the cavity photon starts with any kind of spin which is not TE or not TM, so if the spin is not perpendicular or parallel with the wave vector, in-plane wave vector, then the spin will go a precession movement inside this Poincare sphere. So this is very similar, or it can be analog to a magnet which is in a Bloch sphere with a real magnetic field. So in a Bloch sphere, if you have a single magnet, and if it's initially not aligned with your external magnetic field, it will precise inside the Bloch sphere, which is well known for like a nuclear magnetic resonance, things like that. So this is an optical analog. So once there is a TE-TM splitting, this TE-TM splitting in the optical macrocavity serves as an effective magnetic field on the photon pseudospin. So it's not a real magnetic field, but it's like its effect on the photon pseudospin is analog, or is like to the real magnetic field, the effect of real magnetic field on the nuclear spin or on the electron spin. So the photons which are initially not T and TM will precise inside this Poincare sphere and form this some kind of phenomenon such as what we call optical spin Hall effect, which you show that if you initially put a sigma plus circular polarized light in the center, when the exciton polarity propagates in the in-plane wave direction, you will find it's processing. So it shows alternatively sigma plus, sigma minus, sigma plus, sigma minus patterns changing continuously between this circular, linear, this kind of a state. Okay, so in our lab, we developed a new kind of macrocavity, which is we call open macrocavity. So instead of having the cavity as a whole planar structure, we separate the two mirrors. One we have a bottom DBR mirror which has reflectivity by semiconductors, and on top we grow a quantum well, which has excitons in quantum wells. And also on top, first we etch a concave shape on the top sample, and then we deposit a top DBR which has a concave mirror and it's a round shape. And in this case, we mount the bottom sample and top sample on nano-positional piezo stages. In this case, we can freely tune the optical resonance of the cavity, and we can freely define the shape on them. So we low down this whole thing to low temperature, and we study the optical emissions by pumping the quantum well emission excitons non-resonantly, and the emission from the cavity shows typically a full series of Laguerre-Gaussian modes. And this is three-dimensional tightly confined macrocavities in this plan. And also, if we scan the piezo voltage of this stage of the cavity, so which means we gradually decrease the cavity length, we can see that the cavity mode, when it goes to the exciton energy, it shows anti-crossing behavior with the exciton energy, which shows that this cavity is in strong coupling regime. So those states close to the exciton, they are states with coupled exciton and photon, which are called exciton polaritons, which is a mixed state, or which is a coherently superposited state of light and matter. So it has properties of half exciton, half photons, which half light, half matter states. So in this macrocavity, what we are interested in is this mode 2 or mode 3. So those modes, it's exciton polariton, and those modes, it has optical angular momentum. So first, we study that for the first excited manifold, which is the Laguerre-Gaussian mode. So what is we studied the eigenstates of these modes in this open macrocavities with existence of TETM splitting by the DBRs. So in this case, we put in this, it's like a Schrodinger equation, so we can solve the eigenstate with the perturbation theory. We include this confinement potential of these mirrors and the spin orbit coupling term. Sometimes we put some ellipticity here, but in this slide we just ignore it. So that we have with the spin orbit coupling induced by the TETM splitting, and we get the eigenstate of this. So the eigenstates of this cavity split into 3 energy levels with 4 eigenstates. So the highest energy or the lowest energy, so the 2 split energy, it has the total angular momentum, which means the momentum, the orbital and spin angular momentum, they add together, we have total angular momentum of 0. This state, the conclusion is that those states split, and this corresponds to vector beams of azimuthal polarized spin vortex and radial polarized spin vortex. And in the center, we can have all different kinds of this hyperbolic, like we call hyperbolic like spin anti-vortex. So which with the polarization angle rotates anti-clockwise compared to the real space angle. So experimentally, we can also observe this. So those eigenstates is that we pump the quantum well in the macrocavity, pump it hard, so it can go above threshold to form exciton polariton condensation. So you can think of it similar to atomic BEC. So yesterday there is a talk on Bose-Einstein condensation. It's a condensation exciton polarity, which you can also understand it like a laser, but it's not a pure photonic laser. It's an exciton polarity laser, and so above threshold, when the temporal coherence increases, we see definitely this mode split into 3, and those 3 modes are the eigenmodes of the system. Then we can measure polarization dependent measurement. Then we measure S1, S2, S3, those Stokes parameters. Then we can calculate the intensity, and we can calculate the linear polarization angle of those modes. And we see that those 3 modes are exactly those spin vortex, azimuthal and radial polarized, and in the center it's a hyperbolic like spin anti-vortex. And maybe it's easier to understand like that. So since the system has TE-TM splitting, so for the eigenstates of the system, this azimuthal can be viewed as a pure TE mode, and this might be viewed as a pure TM mode. Well, this one is something intermediate between TE and TM, and it can have different forms of existence. So this is the first what we observe for the first excited manifold. And we also measure a second excited manifold, which is basically with this L equal to 2 4-pi of phase vortex with the Laguerre-Gaussian mode, and they all have J equal to 1. So in principle, those states also split from an eigenstate of this system, and this is something what I call optical skirming. So, which means if it compared to a magnetic skirming, which is have a singularity of sigma minor state surrounded by a sigma plus state environment, so spin down in the singularity in the center and spin up, all surrounded and connected by the transient linear polarized or transient spin in the center. So if you compare the Bloch sphere of magnets with Poincare sphere of photons, then this shows sigma plus circular polarized in the center and sigma minor polarized outside and connected gradually by elliptical polarized and linear polarized. So this is very similar, or it's analog, or we can call it a pseudo skirming, analog to this magnetic skirming states. And we do experimentally observe the split eigenstates in density, and here I just show the polarization map, which is the linear polarization angle. It shows that it's a radially polarized in the center and azimutally polarized at outer ring, and this one is azimuthal in the center and radially polarized as the outer ring. And this kind of eigenstates you can get only in this kind of small, tightly confined optical cavities, but with TE-TM splitting. And based on our studies, we would like to go further. So in Poincare sphere, we can for many quantum optical systems in Poincare sphere, we can manipulate the photon spin or optical spin, and of course for orbital angular momentum, you can manipulate the orbital angular momentum. So why can't we just think about to manipulate a higher order thing? So what I call J Poincare sphere, which means it's total angular momentum Poincare sphere series. So let's take the simplest case with L equal to 1. So angular momentum, orbital angular momentum equal to 1. So to describe this spin orbit couple states, we can use this 4 orthogonal base with angular momentum and spin momentum is either 1 or -1. So it's a vortex, either sigma plus vortex, sigma minus vortex, sigma plus anti-vortex, sigma minus anti-vortex. So any states on this 4-dimensional hypersphere sphere can be defined by a 4-dimensional wave vector, which we can call it coupled spin orbit. And this superposition with this wave vector product, this base, gives you a state. So actually, you can, with this wave vector, you can choose any two of the states which are orthogonal, then you can put them on two poles of the sphere. You can form a higher order Poincare sphere. And this is the pioneer work at City University of New York by Giovanni, and they have published this on PIL. So what we do is discuss a little bit more about okay. It's not very, sorry, because I didn't, this is the last slide. So because in our system, we can observe the splitting between these two, and all those spin vortices and anti-vortices are orthogonal in this space. So we can create this kind of different spheres with different total angular momentum. And the thing is that we have a splitting between these states, and we have splitting also between these states. So we can have a precession of, it's to say that we have magnetic field already exists in this state. So if we initially impinge a state on this or on this, it will start processing in these spheres. And this procession is twice slower than this one because the splitting is different, and while this center phase describes all the unsplit states, there is no procession. So the idea for the further perspective is to manipulate this high-dimensional coupled orbit and spin in this Poincare in this high-order Poincare sphere series, like a qubit or something, and you can use excitonic features of the polaritons to do it, to have to manipulate it. Okay, that's it. Sorry for it. It's not practiced, so sorry for keeping it a bit too long.
That's okay.
Okay, thanks.
Time for one important question.
Yeah, if you.
There are no questions. Do you think?
That's fine. I mean, maybe it's. I have a poster still.
Okay. So I am keenly aware that I stand between you and the coffee break. So I'll try to make this as expeditious as possible. All right, so I'm here today to talk to you about the work that we've done these last few years on plasmonic nanoantennas. By now, from one of the previous speakers today, and of course from yesterday, you all have gotten some idea on plasmonics. And I also agree that in the last few years, the general field of plasmonics and metamaterials is convergent with the field of singular optics. How to use it, I think, is still a little bit something that needs probably a little bit more exploration, but for sure there's, I think, a slow convergence there. All right, so I'll talk to you about the work we do in nanophotonics. My students are here to talk about the biophotonics work during the poster session. In some way, this talk is related to the theme of the conference in small ways. So you'll see towards the end, say something about vector beams as well. All right, so with the nanophotonics work, the outline of the talk will be as follows. I'll start with the background. We'll talk about the application with respect to nanotweezers. We'll introduce the idea of reconfigurable nanoantennas. They're not absolutely reconfigurable, but we'll introduce that idea. We'll talk about another interesting application with regards to what we call plasmonic photography, touch off on some of the work on preferential trapping that we're looking at, and highlight some future directions in the conclusion. So luckily, I think the second speaker gave a good overview of nanoantennas. So yeah, I'm in engineering. And one thing engineers have access to and do really well is fabrication, driven in large part because of the semiconductor industry. So we use electron beam fabrication, which has its limits in terms of what you can do with it. But this is in contrast to what the chemists do with plasmonics, because we tend to go for making array structures, and which could be useful, like in our case, if you're looking for collaborative effects between the elements in the array. So in this case, the basic topology here is to have a two-dimensional array, 100 microns by 100 microns, of gold bow-tie nano antennas. And the term nano antennas here, of course, is borrowed. This is sort of an antenna in the sense that it's still doing some type of transduction between electromagnetic radiation and converting that to energy at a local scale, but except it's more lossy. So at radio frequencies and microwaves, you think of high conductivity. At optical frequencies, we're thinking of high reflectivity. Okay? So this is gold on some adhesion layer that allows the gold to stick to a substrate. In this case, it's either titanium or chromium. It really matters, depending on your application. ITO is typically present. This has to do with the nature of the fabrication process. So ITO stands for indium tin oxide. It's something that you see a lot when you're using e-beam fabrication to mitigate charging effects. Okay? And then we have a thick piece of silica glass. So one of the big reasons people have been interested in nano antennas is because of the field concentration. Get very high field concentrations locally. Okay? If you speak to someone who does not work in the field of nano antennas or plasmonics, the automatic response is it really practical because it's lossy, okay? Which I think is a very fair critique. Okay? So what I'll add on top of that, there was a very nice review article in Nature Nano a few months ago discussing this issue of plasmonic loss. And the author was highlighting the idea that when one has a system where you already have high efficiency, you have to be cautious about how you introduce the use of plasmonics because you likely will reduce your efficiency. But if you're working with a system that's low in efficiency, such as how it's been used in SIR sensing, for example, then plasmonics really has a role. We've sort of taken a slightly different vantage point, and we've looked at situations that don't rely necessarily on an absolute efficiency. And so that's what I'm going to talk to you about today. So this is the basic geometry of our structure. You see the dimensions. We choose that simply to work with the laser wavelengths that we have. The field enhancement that you get when you have a single antenna is on the order of 100. When you put this thing in an array, it goes up by another order of magnitude. Okay? It depends also intimately on how sharp your tip is, so the radius of curvature of that, so you can exploit what's called a so-called lightning rod effect. All right, so recently we did an overview of some of these ideas in an OPN, highlighting, starting off with the application of the nano antennas to tweezing. Okay, so, generically, you're going to optical nano tweezers. So we know that it gives you high field enhancement locally. Your intensity is high, so the gradient intensity is also high. We explored for a couple of years the idea of how to exploit that parameter space for particle manipulation. We found that there were different regimes of particle trapping, and what's very fascinating when you have a landscape that's given by these arrays to the arrays of antennas is that it serves as a multi-physics platform, okay, which makes it really interesting. So multi-physics in the sense that, of course, there's electromagnetics, but there's also heat transfer and fluid dynamics that goes on. Okay? So I throw this up here to say that we looked at some modeling to try to explain some of the fluid dynamics, the observations that we made in optical trapping. Real quickly, one starts off with the electromagnetic problem. All right, so you have the time-independent wave equation and use this to look at the field in the vicinity of the nano antennas, and you determine your heat source density. And so from the heat source density, you determine from each element of the antenna the heat power that's generated, and then you sum that all up for all the antennas that are playing in this game. And then you use that as a source term to help solve your coupled heat transfer fluid mechanics problem. Okay? So we started off with the optical trapping problem. We made this very useful diagram that allows us, it's very robust, very highly repeatable, that allows us to look at a particular number of antennas under a certain illumination spot as a function of your input power. Okay, so we call it a sort of a phase diagram for looking at the different trapping phases that we have in our system. Okay, so one of the degrees of freedom that you have here is that you can change the array spacing. Okay, you may want to do that if you are trying to play games with enhancing the local field. So with really low input optical powers, very low numerical aperture illumination, we've gone as low as 0.25, we've gone as high as 0.6, you can achieve optical trapping and optical manipulation, okay? This is what we see here. We have here a 500 nanometer polystyrene bead. This dark region here, the shaded region, this is on the bright field microscope, is the area of the antennas, okay? The 4 is just so that we know what we're looking at because they have different array spaces. And we are using a standard optical, nonlinear optical microscope setup. So we have a galvo that scans a laser beam. So what we're doing is just scan a circular pattern, and we can drive this particle the way in which we want to on the surface of this, close to the surface of this array. Okay, so keep in mind, this is a few hundred microwatts of input power. This is 5 milliwatts of power, okay? So the idea here is that the power density overall is extremely low. This is part of the reason why the people in physics, biophysics, are very interested in perhaps exploiting this, okay? Now, as you start to move up in power, something else happens. The antennas get hot, okay? And once they get hot, you start to generate natural convection. And that normally that natural convection causes destabilization, especially since the nature of the convection forms a toroidal current. So axially you get destabilization, but you also have some recruitment of the particles in the transverse direction, okay, something like thermophoresis, using this effect. So that extends beyond the illumination spot, okay? So here, what's very fascinating is that if you just have a single particle, and this time this is 1.5 micron diameter particles, you can't trap. Okay, and this is about a milliwatt of input power, all right? Because these things are being destabilized because it's too hot, okay? But if you have 2 or more particles, they disrupt the fluid flow just enough to create axial stability. Okay, so you get now this ability to trap a swarm of particles. And what's fascinating for us, because we know we expect the trapping behavior to be a near field effect, these are basically large particles relative to the wavelength, that we have a stacking of these particles in a hexagonal type of structure. And this hexagonal structure has been observed, of course, typically in a lot of colloidal physics experiments. And we can move this swarm along the array, turn the field off, the particles go about their business. Okay? And we can use this type of scheme to achieve some type of passive sorting as well, which is something that we also looked at. Basically, you can design the antenna structures based on the input optical parameter space to preferentially trap a certain size of particles and not trap another size of particles. So we call that passive sorting. Okay. What's interesting, this also works well when one works with pulse illumination. It actually works really well with pulse illumination. So what we found was that the near field forces seem to be enhanced. We're not quite sure why when one uses the pulse source. So I wrote down there the typical powers that are used here. So we have a 80 nanometer silver nanoparticle, in this case, that we're trapping. 300 nanometers was as small as we can go. Using a CW source, we can go down to about 80 nanometers when we're using the pulse source. Same system, exact same platform. Okay? I'm skipping over a lot of things, but I'll just say quickly as well. It also matters as well the geometry of the nature of how you're trapping. Okay? Are you illuminating from the substrate side first, or you're illuminating from the antenna side first? You get different physics. Okay? All right, and of course, since it's one of the things that people have talked about over the years with nano antennas is enhanced light-matter interaction. So of course, anything where you start to affect the nature of the radiation pattern from quantum emitters or anything like that is very interesting. Here we just have a fluorescent bead. You see off the array, you have a certain luminance. On the array, you get an enhancement of the radiation. Okay, so then we did something else. All right, so totally by accident, okay, which is the best type of science, okay? We were interested in trying to harness the mechanical degree of freedom in the system, which is effectively suppressed when you have antennas bound to a substrate, okay? So here, we introduced the idea of
etching down the glass around the antennas and making pillars out of them. So the pillars, the glass pillars, are supporting the nano antennas. People have done something like that with mushroom arrays and so forth for enhanced surge sensing. Okay? We were looking at it from a different perspective. All right, so here, one of the first things we noticed, you place these guys, you have this array antenna, same type of structure, so now it's a 500 nanometer tall pillars. You place it under SEM illumination, and your eyes are not deceiving you. You actually start to see the antennas actuate. Okay? And you can do this for a single antenna because it's SEM, 1 nanometer beam, or you can do this for a subarray within the larger array. Now, why would you want to do that? Because obviously, if you change the gap spacing, you change the plasmonic response, different optical property, and therefore, in net, the overall surface plasmonic response could be tuned. In short, it's highly repeatable. So you can tune this as a function of the accelerating voltage of the SEM, or as a function of the magnification of the SEM. It turns out that this attractive force is very common if you're using an SEM, a scanning electron beam, more so than the repulsive force, which requires you to come dead center with the beam to do it. Okay, and we'll explain why in our paper. All right, so here's a graph where we just show locally using a supercontinuum source, probing the surface for different gap array distances, and you see the overall reflectance spectrum, reflection response is different depending on where you illuminate from the source. And that's something that we tune post-processing. Why is this also important? Because the resolution using E-beam lithography is on the order of about 20 nanometers, reliably. Okay, we were able to close that gap distance to about 5. We're actually interested in going down below 1 nanometers, because below 1 nanometers is where people also believe quantum effects starts to creep in. Okay, so something else interesting, exact same platform, okay? We've raised this now above the substrate, so it's effectively in air. So it gets hotter much faster, and it gets really hot enough to reflow gold. So even though the bulk melting temperature for gold is above 1,000 degrees C, we see here we can come in with relatively low input optical powers and get temperatures on the order of about 800 degrees Celsius. What that does now is allow us to, again, start to contour and change the morphology of the gold nanoparticles, which in effect leads to a different plasmonic response. So at one point I looked into photography when I was a graduate student, so I started thinking about this from the perspective of photographic film. And here you have this color palette, sort of like the ISO standards. Here are different input optical power densities. You see the change in the reflectivity. This is an SEM showing you the associated response. So one way of looking at this is that this has the ability to record the near field optical intensity. Okay, so this is point one in which this is somewhat related to this conference, which is the idea of using this to even record a vector beam. So you illuminate with a vector beam under low NA conditions, you get the polarization distribution. This nano antennas are highly polarization dependent. So here, this is recording the polarization distribution in the near field, illuminated with a radially polarized light. Here's the polarization distribution in the near field, illuminated with azimuthally polarized light. You can do fun stuff with this as well. So since this behaves like film, except it updates instantly, you can record whatever pattern by scanning the beam, or you can use a spatial light modulator and encode a stickman figure and stitch that back post-processing. So for my 4-year-old son, he says that guy is dancing. He's supposed to be walking. But it's a little bit of a Rorschach test. So that's something else that we did for fun. Also, while you're in the process of having fun, now we say, okay, this is like photographic film. And it's really fascinating. You start to go back and read the type of things that people do with photographic film. There's no reason why you can't record, encode optical information on the surface, audio information on the surface, which is something we also did. Okay, so we use this approach to record different notes and basically take those notes back, basically with a camera, process it, and stitch it together and rearrange it the way we want, and we can get sound, if this plays, let's see. Okay. So my postdoc was into lullabies. So there you have it. So there is a scientific motivation for that. So if you go and look at the paper, what we introduce the idea of doing some level of signal processing on the surface, because now you can record in the time domain or in the frequency domain, so you can actually display the temporal spectrum on the surface and edit your actual spectrum. Okay, so you can delete the low frequencies or delete the high frequencies. In terms of the optical trapping component, here, you can now shape the landscape and bias it. Okay, so I brought up all that stuff earlier. So here, again, we call this sort of optofluidic channels without walls. We write a channel that's in the form of a square wave pattern. We flood illuminate with a 15 micron spot size beam. We have about 1 micron silica spheres in solution. And basically, we find that we can confine the particles to the pre-designed channels that we make in real time. Okay. Again, this is a different flavor from how people have been working with plasmonics. So in our case, we actually try to use the heating effect, what would be another man's loss, to something that potentially would be useful. Okay. All right, so some other directions that we're interested in has to do with acoustic wave generation, which was the original point, actually, for putting it on pillars, because there's a mechanical resonance as well associated with that, right? But now we really have to get into the materials, right? So we observe plastic deformation of something that's akin to plastic deformation of our pillar structures, but we want something that's reversible, okay? And then the moment you can make it reversible, you can perhaps, for instance, excite this at the resonance frequencies. We just get a high rep rate laser, get this thing to oscillate, and you get acoustic ultrasound frequencies. We've started to work in applying this to trapping of cells. We want to be able to sort cells, healthy from malignant cells, on the surface in real time, and actually create those channels in real time rather than going back to the fabrication room and making an optofluidic system. Connection number 2 to this conference, some recent work. We found that we can use this as a platform for generating the tabletop etching. Okay, so literally we can etch away metal in a laser-directed way from the surface and make whatever pattern we want. So we've been able to make a Fresnel zone plate, and we've also been able to make a fork dislocation that gives us angular momentum in this planar structure. This is very different from the meta-surface approach. Okay, this is somewhere in between meta-surface and standard diffractive optics. All right, so those are the conclusions. I talked about some different approaches that we've taken using our same nano antenna platform. And I'll thank my students and the conference organizers for inviting me, and open the floor to questions.
You have a silly question. I'm wondering how large the electrical field strengths are in your, how will they compare to, say, for example, surface experiments that we do on kind of surface spectroscopy? Do you have much knowledge?
On surface spectroscopy?
Well, things like surface enhanced Raman spectroscopy.
So it turns out I'm just coming off of a sabbatical at MIT, and this was actually one of the interesting directions to apply this to SIRS. So here's the challenge. This is why it's very fascinating to look at different fields. Okay, people in chemistry, in particular, are very interested in doing SIRS for a lot of different reasons. But what they tend to do is make dimer structures, which we're calling nano antennas, cooked up in a dish. Okay. The problem is you can only control the chemistry with so much. So you get very high gains because you can get much smaller distances, below 1 nanometers, between your structures. So very high fields. The advantage that we have using our approach so far is that we get something that's very highly ordered and highly repeatable. So the interest in that collaboration is to actually start to look more at doing SIRS type of experiments where you can have very repeatable, very controllable gains. And believe it or not, that hasn't been done. I was actually surprised.
Any other questions?
Yeah. Well, why do you have the triangular shape? Is there something special about that?
Short answer is kind of special to us. It's not really special in the grand scheme of things. So there's certain geometrical factors that people like to exploit to enhance the local field intensities. The triangular bow tie shape tends to be the best one because it has a sharp tip, so we really can exploit the lightning rod effect. And to be honest, it's fairly easy to engineer. But there are other geometries that have since been explored. But so far, bow ties are good because they give high field enhancements.
Okay, on that note, let's thank Kimani and all the other speakers.
It's 2D, but it's